Hi, class. I wanted to talk a little bit more about significant figures. Yesterday, I thought I had a nice, easy way to explain it to you, and I found out pretty quickly that it was not very good. It was causing more confusion than it was help. So I wanted to try again. So what I've done here is I've made a short little presentation to talk about significant figures a little bit more. The first thing I wanted to talk about is why are we even talking about significant figures? I realized I didn't really tell you that, just to introduce them. So significant figures are important because with every measurement we make, there are errors associated with that measurement, right? A lot of it has to do with how precise our measuring tool is, as well as how good we are reading it. But if you remember in the video earlier this week, I showed two graduated cylinders, and we had you could see the liquid in there. And we were looking at the two tick marks. We had to estimate where it was in between the two tick marks. Now, depending on how far apart those tick marks are, will tell you how precise you can get with your measurement. All right, so if you look at the two rulers I have below here, we'll use those today instead of graduated cylinders. The top ruler measures to every centimeter, while the bottom ruler measures to every 1/10 of a centimeter. So it's got 10 times the precision. Right? So if I put a line on my screen here, and I look at just the top ruler, I'm going to look at that line and say, well, it's between 3 and 4. So I know my first digit's a 3, but I need to estimate one more digit. So how do we estimate this next digit? Well, first we're going to say is, does our line appear, does the thing we're measuring, does it appear to be closer to the 3 or closer to the 4? And in this case, we see it's closer to the 4. So now I'm going to imagine that there was a line at 3.5 or a tick mark at 3.5. And then I ask, is the line we're measuring, is it closer to that imaginary 3.5 tick mark, or is it closer to the 4? In this case, I'd say it's closer to the imaginary 3.5 tick mark. So I would estimate this as, let's say, 3.7. I'm going to estimate that last digit as a 7. All right. So we can read the 3. We always should agree on that 3. We're estimating that last number. So I think it's a 7. Somebody might think it's an 8. Somebody might think it's a 6. But that last number is an estimate. We have to do the same thing on the bottom ruler now. That same line in the same place, we look at that ruler, and because this ruler has its tick marks separated by 1/10 of a centimeter, we can read right from our tool what that 1/10 of a centimeter is, and we have to estimate one more place. We have to estimate that 100th of a centimeter. So looking at this bottom ruler, we see it's between the 3.6 tick mark and the 3.7 tick mark. Right? So we can read. We all should have 3.6. Right? The ruler tells us that much. No, we have to estimate that next digit. Right? So I'm going to look at that and say, it looks slightly more than halfway between the 6 and the 7. It's really hard to see real close for what it is when it's that small, that close together. So I'm going to call this number here 3.6766. Let's call it 3.66. So we all should have 3.6 to start with, but that next digit, our estimate, that's the one we're going to be a little bit different with. So this is why significant figures are important, right? We need to know how good our measurement was, how accurate our measurement, precise rather, our measurement was. And our more precise rule in the bottom allows us to give a more precise answer. That's why the rule in the top could only tell us to 3.7, but the rule in the bottom can tell us to 3.67. We have got more precision in that bottom one, right? So there's less error in that bottom one, right? We know we're within a 1/10 of a centimeter on the bottom one. In the top one, we know we're within a centimeter. So significant figures are a way that we show in our measurements how precise, what our error is involved in our measurement. All right. Now we care about that. Your calculator won't. We could type any number in your calculator and do division, and it's going to give you this whole long number because math doesn't care, because math's not doing measurements, right? We're doing measurements. All right. So exact numbers versus estimated numbers. Just a quick one on that. Some exact numbers are things like we counted, right? There's 5 dimes. There's not an estimate there. We don't have 5.1 dimes. You have 5 dimes. If I give you a number, like I say it's a given number, right, then we consider that one exact. We have constants that are exact, like in the area of a triangle, that 1/2, that's exact. And if we give you conversions, those are going to be exact as well. Now, I'm talking about exact to contrast it with estimated numbers. Those are measurements. Those first things here under exact numbers, none of these are measured. None of these are measured. It's the estimated numbers that we need that we're going to work with from measurements, and they need the sig figs. Right, an estimated number, right? It's an observed value, right? We observed it on the ruler, we observed it on the graduated cylinder, and there's always an error associated with every measurement. That's why we have to worry about how precise our tool is and make sure we use all the digits available to us to tell the reader how precise our measurement is. All right. So there's two rules for significant figures. The first one's really, really easy. Anytime you have a non-zero number, it's always significant. Right, so if I write down 247 centimeters, 3 sig figs there, 0.1491 kilometers, 4 sig figs, and on the bottom one, there's 5 non-zero digits. All 5 of them are significant. It gets a little harder when we're talking about zeros, though, and this is where I made things a little bit confusing yesterday. There are 3 kinds of zeros. 3. The first one are leading zeros. Leading zeros will never count as significant. They'll never count as significant. So here's some examples of leading zeros. They're the left of any non-zero digit. None of those zeros are significant, right? So we only have 3 sig figs here in that first number, 0.0000543. Those leading zeros don't count. 543 tells us are significant figures, right? Same thing with the next one. Leading zeros don't count, so only the 9 and the 3 are significant. And finally, the last one, only that far one on the right is significant. Leading zeros never are significant. Captive zeros always are significant. What do I mean by captive zero? It's surrounded by non-zero numbers. So if you look in this example, we have a 7 on one side, we have a 4 on the other side. We have the zeros in the middle. They're captured, they're stuck. So if they're surrounded by non-zero numbers, they're going to count as significant. So in each case here, you're seeing we have zeros in the middle. They always count. So far, the rule's pretty easy, right? If it's a leading zero, you never count it. If it's a captive zero, you always count it. The trailing zeros are the ones where it gets complicated. And the rule I'm going to talk to you about here is only count them if there's a decimal. Only count them if there is a decimal. So here's some examples of numbers with decimals. That first one, that 10.0, we have a 0 to the right of the decimal. Doesn't matter where that 0 is, but we have a decimal point. Those zeros will count as significant. Same thing with the next one. Doesn't matter where that 0 is, it counts as significant. Okay. And finally, the third one, this is a little bit of a different variation, right? Here, there's no zeros to the right of the decimal point. It really doesn't matter where the decimal point is. What matters is simply, is there a decimal point? So in this last one, yes, there's a decimal point. That means those zeros are significant, right? So if I read what I'm saying with that last one, 100,000 grams, that means our scale can read to 100,000 grams. Maybe it's 100,001, maybe it's 900, maybe it's 99,999, but our scale can read to that last digit, to that gram figure. If our scale could only read to the 100,000s, right? Then what's our number going to be? It's either 100,000 or 200,000, right? Our tool is not precise enough. And that's really what you're going to get out of here with significant figures, right? It shows you the precision of your tool. Without a decimal point, the zeros do not count. If it's a trailing 0 with no decimal, it does not count, right? No decimal, no count. No decimal, no count. There are only 3 sig figs. No decimal, no count. Only 1 sig fig. Yes decimal, yes count. So hopefully that helps a little bit as we're thinking about significant figures for the quiz tomorrow. All right, guys. Good luck. If you have any questions, send me an email. Take care. Bye.